Namaskar and welcome to this channel. So today we are going to solve this type of numericals on the basis of what we have discussed in the previous lecture. First we try to understand the questions. So let's get started. In the questions we have given two copper conductors. That means I suppose this is 1 and this is 2. We have two copper conductors having length 1:3. That means if length of this is 1, then obviously the length of this is 3, and area of cross section 3:7. That means if this is 3, then obviously this is 7. So finally we have to find the ratio of drift velocity. Ratio of drift velocity, right? That means this is the ratio. We have to find the ratio of drift velocities in two different cases. First in series, second in parallel. That means these two conductors, first we have to connect them in series, and next we have to connect them in parallel. So in series connections we have to find the ratio of the drift velocity. Also in the parallel connections we have to find the ratio of drift velocity. Alright, so I hope you understand the questions. Now here is the solutions, and which is very simple, and this is the series connections. These two conductors are here connected in series, and these two conductors are connected in parallel here. So this is the series connection, because in series connections I is same, you should remember that. But in parallel connection potential difference V is same. I hope you did understand. The expression for the drift velocity in terms of I is Vd equals I by E and A. This is the famous expressions, but in terms of potential difference, the expression for drift velocity can be calculated by this way. Here F equals ma, which is the Newton's second law of motions. You know, Newton's second law of motion is also valid in this case, because when we supply external electric field to the conductor, the electron inside the conductor experience a force. This force is called electric force, right? According to the Newton's second law of motions, if a particle of a mass m is acted upon by an external force F such that the particle undergoes with some accelerations A, then the force applied can be measured by the product of the mass of the particle and the produced accelerations. This is the condition which is also happening in case of electron inside the conductor when we supply the external electric field inside of it. So F is the electric force. So this force can be written as E times E. This is the electronic charge, this is the electric field. M is the mass of the electron, A means accelerations, acceleration means time rate of change in velocity. Here the velocity means drift velocity and the time means relaxation time. About the relaxation time, that you can see my previous video, or you can follow me on Facebook page 10+2 Hyperphysics discussion forum, where I have completely discussed about it. So this is E and this is E. This is the electric field. Electric field can also further break into V by L. V is the potential difference, L is the length of the conductor, right? L is the length of the conductor. So m is the mass, and this is the Vd, and this is the tau, same here. From these expressions we can manipulate to find out expression for the drift velocity as Vd equals E B tau upon ml. L is the length of the conductor, m is the mass of the electron, E is the electronic charge, B is the potential difference. So finally we have this expression Vd equals E E tau upon m into L. Now we have to compare this expression with this and compare this with this. So what we have seen here is on applying this expression in this case, we have seen that I is same because this is the series connection, so current is same. So E is the electronic charge, so this is the same for these two conductors. I is same for these two conductors. N is the electron density. These two conductors are the copper conductors, so electronic density same. So A is different here. This is the A and this is the A. So these two A are different, right? So we have seen that BD directly proportional to 1 by A. This is the relations. And if we compare this expression with this connection, we have seen that E is same, electronic charge is same, potential is same because in parallel connection B is same. So B is same for these two cases. Tau is the relaxation time. So this is also same for the electrons inside of these two conductors. M is the electronic mass. This is also same, but L is different because in the questions we have a different L. So we can express these relations. Comparing these connections, we can write BD proportional to 1 by L. This is the simple case we have derived here. So finally, applying these conditions with the questions we can write, that means we have to find out the ratio of drift velocities here. So this is the BD1 upon BD2 if we suppose, then obviously from these relations we can write this 1 by A1 upon 1 by A2, and that means A2 by A1. So under putting the given value, we can express this relation finally. This is the answer of first case, and further in the same way we can express the ratio of drift velocity. This is the L, this is the common general expression. So applying these common expressions under two cases, we can express like this. So 1 by L1 upon 1 by L2, that means L2 by L1. L2 is given, that is 3, this is 1. Finally we have expression for the ratio of drift velocity and this and this. So we have calculated this is purely for in series connections, and finally this is purely for parallel connections. Thanks for watching.